So what we want to look at today is what are called quantiles, or they're also called K-values. What we looked at in the past, we looked at standard normal distribution. And in that whole process, what we were finding with that and also with the normal CDF function is we were finding probabilities that a score would be in a certain range, okay? What we're doing here is kind of the opposite of that, all right? And I want to show you the part that I added here. I wanted to show you kind of how you would have to do it by hand. But I also want to show you, obviously, how to do this with technology, okay? We'll start with the technology on some basic examples. Then we'll look at a couple by hand. And then we'll go back to using technology and do some more advanced examples, okay? So basically what we have here, we have this function called the inverse norm. All right, the inverse norm function on the calculator. And those of you who have had a little bit of calculus before, you remember when we did normal CDF, the calculator was doing an integral there, okay? The inverse of an integral is a derivative, all right? So the calculator is using some derivative functions here in order to help us figure this out. But what this is used for is finding a score that has a given area or probability below it, okay? So for example, here we have X being distributed normally, and the 7 is what again?
Mean.
That's our mean. And let's change that back. Okay, so 7 is our mean, and the 2.25 is our variance, okay? What squared gives us 2.25?
The variance squared.
What is the standard deviation? 1.5, okay? So you could write this as 7 comma 1.5 squared to help yourself out a little bit, okay? So our standard deviation in this case is therefore 1.5. Okay? Now, it says the probability that a random variable x is less than a value k is 0.63. So what is k? All right? Well, let's think about this. It's the probability that we're below k is 0.63. So since that's bigger than 50%, I know that the value that we're looking for is going to be somewhere to the right of my mean. Okay? I know the mean is 7. All right? And by the way, this can be helpful here to make sure that you actually get an answer that makes sense. Think about your mean and your standard deviation. If I were at 8.5, okay, approximately what percent of my data would be below 8.5?
34.
34 plus 50, so 84%, right? Okay, just to illustrate that, 8.5 up to here would be 34 plus the 50, so that would be 84%. We only want 63%. All right? So I know my answer, my value of k, has to be somewhere between 7 and 8.5. Okay? Does that make sense? All right? Doing that quick mental check, this is in part why we learned how to do that stuff in those general values, the 68, 95, 97.5, or 99.7, sorry, was to help us as we do these types of things to make sure our results make sense. Okay? So if I'm trying to find this, the area below K is 0.63. Okay? So I'm going to use this inverse norm. If you have an n-spire, you could just type in INVNORM. Okay? But notice up above here it says the area below needs to come first. So I'd put the 0.63 in first. Then the mean, 7. And the standard deviation, 1.5. Okay? Now, this function, the inverse norm, if you go back to your distributions, all right, on the calculator, remember hit second distribution, it's above vars. Okay? It's above vars. Okay, let's bring this up here. Show it once. Okay, so we have second vars, and you'll see number 3 is inverse norm. Okay, now if you have an 83, it's not going to bring up this menu for you, so you're just going to have to remember the area below comes first, then the mean, then the standard deviation. Okay, if you have the 84, then if you have the 84, then it brings up the little menu here, the 0.63, the 7, the 1.5, okay, and you just enter those and hit paste. Notice if you have the 83, this is what's going to show up for you, okay, you'll type it in like that, hit enter, and we get here 7.49778. Okay? So 7.49778. Alright, so let's set that aside here. So now I know that the value I'm looking for, 7.49978, okay, or to 3 significant figures, 7.50. Okay, so 7.50 is the value that we're looking for. Okay, does that make sense? Okay, now the wording on these you have to be a little careful about. All right, the second example here, in the standard normal distribution, what z-score lies above 38% of the data? Okay, so first of all here, you have to remember what the standard normal distribution is. Our z-scores are distributed normally, and what's the mean in our standard normal? What?
0 and 1.
Okay, it's the mean was 0. The standard deviation is 1, so we've got 1 squared in here. Okay? Remember how we did that. Okay? We took all the scores. Remember our formula for z is z equals x minus mu over sigma? Okay? Well, let's think about that. If we take all the scores and we subtract a value from it, what does that do to our data? The mean and standard deviation for our data.
It shifts it over.
It shifts it over. So what would our new mean equal
If what?
if we subtract the mean from all the scores?
0.
0, all right? Remember, if we subtracted 5 from all the scores, our mean would be decreased 5. If we added 10 to all our scores, it would go up 10. If we subtract the mean from all of our scores, it's going to make the mean of our new set of data 0. Now, what happened to the standard deviation?
Doesn't change.
It doesn't change, okay? So, in order to change the standard deviation, which also changed our mean, we multiplied or divided by something, okay? Now, if our standard deviation is sigma, what would I have to do to get my standard deviation to equal 1?
Multiply by 1? Or
Not by 1.
Isn't that
by 2? Wait, what
by
happens
1 over?
how do you get the standard deviation to change again?
By multiplying or dividing all the data by something. What were you going to say?
If you multiply by 1 over itself.
Okay, if a standard deviation is sigma, then if we multiply by 1 over sigma,
It's going to cancel it out.
the mean will be 0 over sigma, so it's still 0. But now the standard deviation is sigma over sigma, which is 1. Okay? That's where that standard normal distribution comes from, those z-scores come from. If you remember that video we watched, the man in the video did develop that, but he did it pretty quickly and didn't really explain it. Okay, but that's what we're dealing with here. So, we want the z-score that lies above 38% of the data. Okay, so let's see here. Our mean is 0. Okay, I want it to be above 38% of the data. So here's data, and once I get up to 38%, I want to stop. So I want this z-score. How do I know it's going to stop before I get up to 0?
Because 0 would be 50%.
Exactly, 0 would be 50%. Okay, good.
It's weird trying to put in perspective, like 50% is 0.
Mm-hmm.
Anything below 50 is like a negative number.
Yeah, well, yes, it is. Because you're talking about, remember, z's are standard deviations. So 0 is right on the mean. So a negative just means that we're below what the mean was.
So to the left of the
To the left of the mean, yeah. Okay. So now we just do inverse norm. And what are we going to put in?
0.38.
Okay.
0 and 1.
0 and 1. Good. And we know our answer should be negative. It's negative point what?
So why were we talking about all this process if we're just using the same 38% for area?
I just wanted to remind us of what our standard normal was and where that came from. Okay. All right, what do we get here?
0.305 negative.
Negative 0.305.
Yes.
Okay. Is that what others got?
Yes.
All right. Good. Good. Now, by the way, you'll notice you might have noticed I wrote down the 0 before you guys gave the answer, and it's not just because I had seen it before. But why logically does it make sense that our z would be between a -1 and a 0?
Because that little portion is only 12% of the lower half.
Very good. Okay. That portion here between the z that we're getting and 0 is only 12%, right? And if we were 1 standard deviation away, it would be about 34%. Okay? So since I know that there's only 12%, I know I'm within 1 standard deviation of the mean there. Okay, so the z I'm looking for is going to be greater than a -1, but less than 0. Okay? So again, use that logic, use that thought process to help you check yourself.
So why is it just why is it less than 0? Why doesn't it just go, because it just says above 38% of the data.
The score is above 38%, which means there's 38% below the score. That's where I said you have to be a little careful with the language.
Can you repeat what you said about the point 12? I didn't catch that.
Okay, we know everything up to 0 is how much?
50%.
50%. Okay? We also know that if we were at, remember what we learned about the normal, if we are at -1 standard deviation to +1 standard deviation, that's approximately 68%, which means that left-hand side would be 34%, okay? Since this was only 12%, we're 12% below the 50. I know that if I were at -1, -1's gonna be somewhere over here.
Does it have to be 25%?
No, it'd have to be about 30, it would be 50 minus the 34, so it'd be at about 16%.
The one?
Yeah, at -1, it's approximately 16% below that -1.
So
So-
we know it can't be more than 0.34, negative 0.3, or less than, in that case.
And they're in like three.
Well, we don't know exactly what it's gonna be, we just know it's not gonna be, if we got something like a -1.2, we know that's wrong. We did something incorrectly.
So the
you know.
numbers are separated by 34 increments.
Remember what we learned, the 68, and then from -2 to +2, that was 95%. And then from -3 to +3, that was 99.7.
Yeah, but like the 0 to 1 is 34, and then 1 to 2 is 34.
No,
No?
that's 34, okay? And then from 68 to 95 is 27%,
Oh,
right?
yeah.
So that's
I remember.
13.5%.
I don't
and
like that. That messes me up a little bit.
Yeah, well, it's just, remember, this is just at this point a guide to help us double check our work, okay?
So let's say that they said in a standard normal distribution, what z-score lies above 64% of the data.
Well, if that were the case, 64% would be like over here. But remember, that wouldn't be enclosed, that would be from -infinity up to whatever score we were at. So you still couldn't use like just the standard deviation there. Okay. All right, now let's look at, this will kind of give us an appreciation for our technology here, okay? If I were to redo that first problem, okay? It said the probability that x was below a certain value, it was the probability that x was less than k equaled what? What was it, 0.63 on our first example?
It's, 60, yeah.
0.63. And we knew that we were trying to find that x value, right? Well, if we didn't have our calculators, we would have to use this standard normal table, okay? And we'd have to look at, okay, 0.63, yeah, the closest we can get, it looks like, is right here, okay? Which would be a z-score of 0.33, okay?
Why is it 33, I'm sorry?
Because if you look across here, there's the 3/10 and 3/100.
Isn't it, wouldn't it be like 3/4?
Well, that's the thing, at 3/4, we're at 0.63, huh?
Can't you just subtract it?
What? Subtract what?
Oh no, so the
Like one
z-score
minus-
is just the, you see the, on the very left, how there's the 0.1, 0.2, 0.3?
Yeah.
That's the 10th place of the z-score, and then the 100th place is the top, very, very top, so you just add those two together. if that makes sense.
So how do we assume that the z-score is 0.33?
Well, because we're looking for 63%, right?
Yeah.
And right here we have 0.6293. This
So
is,
you find it the opposite.
yeah.
Okay.
Yeah, rather than looking up a z-score and finding the probability, you've got to look through this whole table and find the probability you're looking for, or as close as we can get to it, and then use that. Okay?
Do
So,
we always write x less than k?
yes, the inverse norm will always be for x less than the value. And we'll look at some in a moment where it's not less than, and see how to handle that, okay? But here, notice what we have to do. At this point, what was the mean and the standard deviation for that first problem again?
The mean was 7.
Okay. And standard deviation was what, 1.5?
2.25.
Well, that was the variance, right? Okay.
Too many smart things in a row, like I gotta.
So here is where our z formula comes into play. X minus mu over sigma. We know z is a 0.33. The x is the k value that we're looking for, but we know the mean is 7 and the standard deviation is 1.5. And now we could solve for what the value is.
Reverse.
Okay? Yeah. So you multiply by a 1.5, and we've got a 0.495. Is that right? Hang on. 165 times 3.
Yeah, that's right.
Okay, yeah. And then that's k minus 7, so k would equal 7.495, which if you rounded to 3 significant figures, again, would give you 7.50. Okay, which is what we got. Okay, it's just this is obviously more complicated and it's less precise because we didn't have a value that was exactly 63% in our table.
So what we're doing now, we're proving what we got, right, with the
Yeah,
inverse norm.
We're kind of showing if we didn't have our calculators, what would we have to do?
But on the questions like this, we'll have our calculators on the test and everything.
Yes, you will.
Okay.
Okay. This is just kind of one of those help us appreciate our calculators types of problems. Okay? All right. Let's try this one here. Okay? In the standard normal distribution, what value of z would show us where the top 35% would start? Okay? So the top 35%, that means at this point, notice here it says the probability x is greater than k is 35%. So, here's k, here's 35%. Okay, so what are we going to have to use?
The 1 minus.
Yes, we're going to have to use the complement here because our inverse norm always takes the area below. Okay, so I've got to use that 65%. If you think about it, the inverse norm always takes the percentile. Okay, if you remember what the percentile was is the value that you're greater than. Okay, so it always takes a percentile.
So, Mr. Hickson, so why do we draw this out this way? Why do we have to find sometimes this part and sometimes the other part?
Well, it's just the way it's worded. Where the top 35% would start indicates that the value we're getting is below 35% of the data.
Okay.
So it's just, you just gotta be careful with the language there.
Okay, but do we have to subtract 1 minus 35, 0.35 or no?
Well, yeah, you do for in here. You have to get
0.65.
Yeah. Otherwise, if you did the 0.35, you would actually be finding this value, okay? Where 35% is below it.
So when they ask on the top, that's when we subtract from 1, right?
Mm-hmm, yeah. So here, we use this, we use 0 and 1, and we'll get our result, okay? Okay, so we got inverse norm, 0.65, 0 and 1, and you get a 0.385. Okay, so here's our 0.385. So to be at the 65th percentile, you would have to have a z-score of 0.385. By the way, without doing it on your calculator, what would you have gotten if you had punched in 0.35?
The opposite of that.
The opposite, okay? It would have been a negative 0.385, okay?
Question 35.
Yeah, if we would have put in 0.35 instead of 0.65, we would have gotten a negative 0.385, okay? Because we would have gotten 35% below instead of 35% above. But that's where if you catch yourself doing it, you don't have to recalculate it, you can just understand it, okay? Yes? All right, this one I want you guys to take a couple minutes and try. You can work together on this one. We have the mean of a set of data is distributed normally, of data that is distributed normally is 76.5. So X is distributed normally 76.5, and the standard deviation is 5. Okay? Then 45% of the data lies between 70 and what value? Okay, so here's our 76.5. Obviously 70 is right here. 45% of the data lies between 70 and what value? Okay? In other words, the probability that X is between 70 and K equals 0.45. Okay? So take a couple minutes, work this one out, and see what you come up with. Alright, so how would we go about figuring this out? Where would we begin?
I got a number, I'm not sure if it's right though.
Okay.
I didn't use 70 at all.
You-
I found the z-score.
You found the z-score?
78.75, which I thought might work.
Okay, so what how did you get a z-score?
I did 0.45 is equal to k minus 76.5 over 5. And then I found k, and it was 78.75, so I was like...
Okay, so what do you guys think about that? Using 0.45 as a z-score.
I don't understand why we would.
Okay. What do you think?
Why?
Well, that's kind of what I'm asking. Do you guys, is there a reason why not?
I don't know, the answer is like logical. She said like 78, like it's just a little above.
Yeah, I don't know if that was the right thing to do,
Well-
but I got a number and it kind of sounded okay, so I was like...
Okay, and that, I mean, it is a reasonable answer there. Okay, our method here isn't really what we need to do, because what you're doing is you're using the probability as a z-score. Okay, what is a z-score?
Standard deviation
Is it
from the
like
mean.
the
It's the standard deviations away from the mean. Do we know that K is gonna be 0.45 standard deviations away from the mean? No, okay. So that's not a bad thought, but that's not gonna get us what we need in this case. Okay? All right? So, does anyone have another idea?
Could we find I don't know if it's relevant at all, but just what I was thinking, you can maybe find the inverse norm for up to 70.
Okay. Find the inverse norm up to 70?
Yeah,
What does the inverse norm give you?
that gives you the area that is like up to that number, so it would give you what's to the left of that 45%.
Okay, you got the right idea, but you're using the wrong function here. We do want to find this area. How would we do that though?
Normal CDF.
Normal CDF. Okay, remember inverse norm, you have to know the area and it will give you the score. If we know the score but we want to know the area, that's going to be normal CDF.
That's kind of what I thought to do. I thought to find like the numbers, like with normal CDF, to find like something till the 70 and something till the K. So like, I'm not sure how I can find the till the point of K in order to find like the like in order to subtract them and get the full one. That's kind of what I thought to do, but I just didn't know how to do it.
Okay, well let's start with this, okay? What would we put in as our lower bound for the normal CDF?
A really small number.
Yeah, a really small number. I mean, in this case, we could use 0. That's going to be like 15 standard deviations below the mean.
But can we
You can use negative 999 or whatever. Okay.
Wait, should we actually use that? So we'll write it down and not only like erase it?
Yeah, you can use anything as long as it's a whole bunch of standard deviations below your mean. Okay?
Can I do -1?
Sure. Okay? Now, when you do this on your calculator, what do we get for that area?
I dropped my calculator and asked in the kitchen.
That's not good.
No. I dropped it in the street and was like, oh my god, is that a laptop? I'm like, no, where's my calculator?
Is the answer we get, is that the area if I like?
Yes.
So 0.097.
Okay, 0.9, let's do 3 significant
6, 8.
figures, okay?
968.
968. All right, so what that means here is while there's 45% between 70 and K, there's going to be, or there is, 9.68% below 70. Yes?
I'm sorry, I just forgot real quick what the difference between normal CDF and normal PDF is.
Remember, PDF is for graphing. We're never really going to use
So we're
that.
not going to use normal PDF?
No.
Okay. So normal CDF is basically, like normal CDF and inverse norm do the same thing just with different numbers.
They do it in reverse.
Like they find, it's almost like the same, like you plug in the same thing except like if you don't have the area for inverse norm, then you would use normal CDF when you have the probability.
Normal CDF is when you know the values, but you want the area. Inverse norm, think it's an inverse for a reason, is when you know the area, you want to find the value.
Oh, so it's like inverse normal CDF, basically.
Yeah, kind of like that.
Now you use inverse norm, right?
Okay? Yeah, now, here's where we're going to use the inverse norm.
So what we found, that's the area, right?
That is the area below 70.
Okay, and 0.45 is the area between 70 and K, right?
That's correct. All right? So we're going to find K by using the inverse norm, and what area are we going to put in?
The sum of the 0.9.
There we are, the
9.
sum of those. The sum of those, the 45% plus the 9.68%. So we've got a 0.5468. Okay? And then of course with the mean and the standard deviation. okay? Because what we just found is that this total area below is that 0.5468. Okay, and remember on a multi-step problem, don't round anything until you get to your final answer. Okay. So now we plug in
It's 77.087.
77.087. Okay, so if we go with 3 sig figs, we'll have 77.1. Okay? And that's a reasonable answer. Okay, we know it's going to be above the mean, not too far above the mean.
That's the answer.
That's our answer. Okay?
My other question.
So that's our idea here. That's what we've got to be able to work through, okay? So we've got different calculator functions that you've got to be able to know. And this might be a slide that you come back to, okay? Normal PDF is for graphing. When are we ever asked to graph these accurately? Never, okay? You're asked to sketch them, all right? But you don't need to use normal PDF to make a sketch, okay? Normal CDF is when you know the score, or you could say you know the K, and it's going to give you the percent. All right? The inverse norm is when you know the percent, it's going to give you K.
So you should probably memorize these.
Yeah, you should memorize, what the normal CDF and inverse norm. No, we're not going to use inverse norm. Those of you with the 84s with the menu, you have a little less to memorize. If you have the 83, you're going to have to memorize what order those go in. Okay.
I have 84 plus.
Okay?